Okay, so moment of inertia question. The question asks, what is the moment of inertia about an axis through the center of a sphere of radius capital R and mass m and density varying with radius as rho equals AR? So this is a pretty tedious problem, mostly because of the fact of a varying density. So we're going to go through this, and hopefully it'll make at least some sense. And if you're struggling with a problem similar to this, maybe it'll be a little easier. So let's get zoomed in, and let's get started. Well, we'll start, I guess, from the top. The general equation for the moment of inertia, when we don't, a lot of times you'll be given a formula sheet, but for something like this, where it's kind of general, you can think it as the integral of r, I'm going to call it perpendicular, squared dm. And just a reminder, the r perpendicular is going to be the distance from whatever mass part of the sphere we're looking at to the axis of rotation. So, and dm is a small chunk of mass, and I think it'll actually make a little bit sense. I don't think they have a spear shape here, but it's okay. If I draw it out. So we'll do blue, I suppose. Do we have a dark blue? We do. Let's do that. I like having options. Oops. So, and let's make this a little bigger so we can see it. Shape, spear, or circle, I suppose. Okay, you can just kind of imagine that this is three-dimensional. I know it's not, but regardless, I think it will work for now. So I'm going to go ahead and draw our axes. We'll be rotating about the z-axis. Okay, there's our y. And there's your x-axis. Okay, now let's draw the best that I can a little chunk of mass here. And this might get a little messy, but hopefully it'll work. So we have two distances, both r, that go out to some part, and this is your chunk of mass, if you will. And actually, before we do that, we should probably mention, looking at this integral here, the dm, you don't want to integrate with respect to dm. That's going to be not good. Instead, what we'll use is the fact that density is equal to mass over volume, or mass is density times volume. Now, density, we know, is just rho of r times the volume. And if we write it as a differential, you could think of it as this. So this dv is what we're really interested in. We want this chunk of volume in this little square mass we're taking out. We want to know this small piece of volume. So that's really the point of this drawing. Because now, if we were to look at our integral, r squared perpendicular, well, we still don't really know what that is yet, but that'll be clear, times rho of r dv. And the goal of this picture is to hopefully let us see what r perpendicular is, as well as dv. So let's continue. Now, this little bit here, we'll call this angle theta, meaning from here to here is just d theta. It's a small little bit of theta, as we have this very small chains. Oh, didn't want to do that. Please go back. There we go. And then this line right here, I think we can see using right triangle trig, I'll put it even here, is r sine theta. That's this part. Okay. The next thing I want to do is I'm going to attempt to project these down at least a little bit. So this is just the projection down. It would be like a shadow casted down. And the angle from your, so we labeled the angle from your z-axis down, theta. There's also this angle from your x-axis to your y-axis, which we'll label phi. And by similar logic as the theta, you can probably see that that's d phi. Okay, well, hopefully that at least makes sense what we're drawing so far. Now we can make some conclusions about it. First off, hopefully you can see our perpendicular is going to be r sine theta. And that's the perpendicular distance from this point to our axis of rotation, which we're rotating about the z-axis. So, okay, now we have something for this. We also need to know that volume element. Well, you can think of it as volume is length times width times height. And if we want the length and the width and the height, it's not a very good three-dimensional drawing, but I think you get what we need there. Well, we have a couple things here. We have r d theta. So that is here and here. You can think of it as the arc length, right? If you don't remember, arc length is equal to r theta. So that's that bit. Well, what else do we have? We have r sine theta. That's from here to there. R sine theta d phi, right? Because that's this angle here. And if you were to project this down, this length will be the same, the length up here will be the same as it is down there. So if you want to think of where the phi is, you could also think of as the phi as being projected moving that way. So you have r d theta, r sine of theta, d phi, and then we just need that last little bit. So you have essentially your length and your width, and then finally dr for that little bit of thickness. And that's your volume element. So hopefully, at least you kind of see, it's kind of hard to draw it nicely to see where it is, but that's where this stuff's coming from. You could also remember this if you'd like for spherical coordinates. But if you didn't, that's just a kind of awful derivation of it. But now that we have all this, we can actually work with our integral now. Now, as you can see, we have not a variable or one variable to worry about. We have three. So what we're going to do is form a triple integral from r equals 0 to r equals capital R. So that's just your radius. So from here to shooting up, theta, well, theta, we're going to go from here down to here. So we're essentially getting half of it. In other words, we're going from theta equals 0 to theta equals pi. And then what phi is going to do is phi is going to wrap all the way around the sphere. So it's kind of hard to think about, but imagine it wrapping all the way around the sphere. Your phi will go from 0 to 2 pi. It goes all the way around. And that'll give us everything we want. Okay, well, our perpendicular, we notice this is the distance from our volume element to our axis of rotation. So that's going to be r squared sine squared theta, right? Just going ahead and squaring it. Rho of r, that was given as just AR. And then dV, you get r squared sine theta dr d theta d phi. Oh boy. So I'm just going to break this up as nicely as I can. One easy way to do this is to think of it like this. R equals 0. R equals R. Let's see. R to the 4th, it looks like. R to the 5th, actually, because there's that extra R. And I'll go ahead and factor out that A. R to the 5th dr. Doesn't really matter where the A is. Theta equals 0. Theta equals pi. We're going to have sine cubed of theta, d theta. And then finally, from 0 to 2 pi of just d phi. So we took this kind of triple integral, and this is a pretty easy triple integral in the grand scheme of things. You can think of it as just 3 integrals in this case. So usually they're not always this easy, but in this case it is. So let's go ahead and actually do these. This will be 1/6 AR to the 6. This one, I just kind of threw in a calculator, but it's going to be 4/3. If you had to do that, then I would probably break this up as sine squared theta times sine theta. Maybe do like a power reduction formula and then some trig stuff, but I don't really want to make this a Calc 2 video, so just trust me there. It's what the computer said. And then this one's super easy. We know that's just 2 pi. Okay, well, let's see what we have. We have 8 pi. That A r to the 6 over 6, 12, 18. We can simplify that a little bit to be 4 pi A r to the 6 over 9. Well, that's all well and good, but the next thing that you might be curious about is the A. What is the A? Well, unfortunately, we have more work to do because we're not done yet. So a good formula to know is that your mass is equal to the integral of our density function times dV. Well, the good news is we kind of already did a harder version of this. So working this out, you'll get the integral of r equals 0, r equals r, the integral of theta equals 0, theta equals pi, and phi equals 0, phi equals 2 pi. We'll have AR cubed, because you have r squared from the dV and then the r from the rho, sine theta, dr, d theta, d phi. Great, another triple integral. So we'll again break this up into 3 separate integrals. Kind of an easy way to think of it. And I'll factor out the A, r cubed dr, and then we just have our sine theta, d theta, okay, well, doing this, we'll get 1/4 A r to the 4th. Let's think about this one. Sine of theta, the integral of that is negative cosine theta. Negative cosine theta evaluated from pi is -1, but negative 1 is +1. So 1 minus negative cosine of 0, that turns to a positive. 1 plus 1, 2. And then once again, nice and easy, 2 pi. This 4 will cancel with the 2's. And the mass equals AR4. times pi. We're solving for this. A equals m over pi r to the fourth. So now we have A in terms of m, pi, and r, which is good because if we scroll back to the solutions, you'll see they don't have an expression for A. So if you did that first part and then you're like, well, gee, I can't see it, I just see m's and r's, you need to relate A to m and r and other things, which is what we did. So now let's go plug this into our integral, or not our integral, our moment of inertia. I, same thing, right? So it was 4 pi a r to the 6 over 9. But now we know what a is. So let's plug in for a. M times pi r to the 4th, r to the 6 over 9. The pi's drop. This drops with a 2 left over. So the moment of inertia will be 4/9 mr squared. And that's in the terms we need. 4/9 mr squared. 4/9 mr squared. So, again, just to review, we set up our moment of inertia integral. We found the perpendicular distance from our points that we're interested in to the axis of rotation. We represented our dm as rho of r dv, and then kind of crudely, I showed us what dv is through some little bit of geometry, in case you don't remember it or it's not something that's provided. Then we had to solve a triple integral, which nicely broke down to 3 single integrals to get an expression for I. But if you go and check, you'll notice that a should not be in the expression. So we used the fact that mass is the integral of our density dv, and we evaluated that, which was very similar to the last triple integral where it breaks nicely into 3. We evaluated it, and then we solved for a in terms of m and r. We substituted that back in and then simplified. So if you're ever dealing with a moment of inertia problem with varying density, you're going to have to do a triple integral. And luckily this one was pretty easy, but at least we got it done. So